In today's video, we're going to explore the concept of specific latent heat and see how to use it in calculations. In the last video, we saw that as we heat up a substance, the particles gain energy in their kinetic energy store, which increases their internal energy, and since temperature is just a measure of the average internal energy of all the particles in a substance, heating something usually increases its temperature. But the whole point of this video is to show that there's an exception to this rule when a substance changes its state. If you look at a graph showing how the temperature of a substance changes over time while being heated, you'll notice it's not a straight line. That's because at the melting and boiling points, the energy we're supplying is used to break or weaken the bonds between particles, not to increase their kinetic energy. And since temperature reflects kinetic energy, it stays constant during the state change until the whole substance has completed the transition. The same thing happens during cooling, except this time, bonds form and energy is released, which again holds the temperature steady through the phase change. The amount of energy needed to do this without changing the temperature is called latent heat, and it depends on the type and amount of substance involved. To make it simpler, we use something called specific latent heat, which is the amount of energy needed to change the state of 1 kilogram of a substance with no temperature change. When cooling, it refers to the energy released instead. There are two main types: specific latent heat of vaporization, which applies when going between liquid and gas, and specific latent heat of fusion, which applies when going between solid and liquid. So imagine we have 1 kilogram of water and we heat it from -50 degrees Celsius to 150 degrees Celsius. First, its temperature rises steadily. But once it hits 0 degrees, the ice starts to melt and stays at that temperature until it's all liquid. The energy needed here is the specific latent heat of fusion, which for water is 334,000 joules per kilogram. After that, the temperature rises again until it reaches 100 degrees, where it begins to boil. Again, the temperature stays constant while it turns to steam, and this energy is the specific latent heat of vaporization, which is 2,260,000 joules per kilogram. After that, the temperature keeps rising like normal. Remember, you don't need to memorize those numbers, they'll be given in exams if needed. And if we cooled the water instead, the same amounts of energy would be released at each stage. The equation to use is energy equals mass multiplied by specific latent heat. A typical example could be, how much energy is needed to completely boil 2.5 kilograms of water at 100 degrees Celsius? Since it's boiling, we use the latent heat of vaporization, so we multiply 2.5 by 2,260,000, which gives 5,650,000 joules, or 5,650 kilojoules. And that's it for today's lesson. If you found it useful, do like and subscribe, and we'll see you next time.